What's up, guys? Nitty Gritty Maths here, and today we're going to do Euler's identity. And if you guys don't know Euler's identity, you're in the right place. We'll show you what it is, and to be honest, there's not anything you can actually, per se, use it for. Or the equation here is e to the ix cosine x plus I sine x, or rather pi. So here we have the equation. Let's look at to the x, not a pi, not yet. So I will just put parentheses around the angles. I'm kind of used to that. So what we have here is Euler's identity, which it's for complex analysis, and we can use this for any real number x. And when we use x equal to pi, there's a special case for this. When in a complex plane, the consequence of multiplying by I is that if you have a graph, and we'll say this is the imaginary, this is the real, you rotate by 90 degrees every time you multiply by I. So whatever, that's a multiplication symbol there. If you multiply by I, you rotate by 90, rotate by another I, and get 180. So that is what we're going to do here, 180. That's what pi is. So what we are going to get here is e to the pi cosine pi, since we're using x in wherever x is, we're putting a pi there, I sine pi. So what we have here, we know sine of pi is 0, cosine of pi is 1, or negative 1, and what we're going to have here is e to the I pi equals negative 1. And that is where the beauty lies in this identity. We can further simplify this, which we have almost nothing else to simplify. E to the I pi plus 1 is equal to 0. And that is Euler's identity. Looking at it first glance, you're going to be like, what do I use this for? Well, to show you, there's so many things in this identity that's so useful. And to start off, I'll say there's a lot of stuff, so we'll just do around like 5 of them. There's the additive identity, where if you add any number to anything, it's going to give you the same number, which is 0. So the additive identity, 0. There's the multiplicative identity of 1, which you multiply any number by 1, you're still going to get the same number x. So that's 2 identities already in this identity. The pi is just gives you 3.1415. It's the transcendental number. If you guys don't know what transcendental is, it's one of those special numbers that are irrational, but you can't express them in a formula. So like, it's irrational, but numbers such as square root 2 can be represented as an equation such as x squared minus 2 is equal to 0. You can express square root 2 in that equation. You can't express pi in an equation. It's a transcendental number. Another transcendental number is e, which we will talk about, which is in the equation, and the golden ratio, which is 1.6 going on going on forever. So another one is the e, which is the base of the natural logarithm, and that has a value of 2.718. And the final one, the identity we will talk about, is I, the imaginary number, the square root negative 1, which we call in the complex plane. We have a whole axis for it, and what I want to talk about here is it's not a practical application what Euler's identity is, which I will rewrite for you here. Instead of this square root 2 business here, we will write e to the I pi plus 1 is equal to 0. And that is our Euler's identity. It's just an achievement of all the advances in complex numbers, algebra, geometry, and arithmetics. Like, we got this identity using other identities from trig, and just using, so this is a connection between the complex numbers and trigonometry, and it makes sense why our complex plane rotates by 90 degrees when we multiply by I. And a really good thing by using these equations here, which I'll show you, I'll erase the rest of this, and Euler's identity, we'll see you in a little bit. It's going to be right here. So we'll say sine of x is equal to the imaginary e to the ix. Yep, e to the ix. So that's useful. And cosine x is equal to the real e to the ix. So what we have here is something that's really useful for us, because when we graph something out here, I'll draw the graph. We'll draw our circle. Boom. There's our circle. Not a good circle, but it is a circle. We're going to have a line here, and we're going to have another line here. If you want me to zoom in right there, here's our triangle. And we will call this, let's call it gamma. I will say this is sine of gamma, or rather alpha, not gamma. Gamma is up, and that's alpha. And we'll call this side cosine of alpha. And the axis here will be imaginary. The axis here will be real. That's why we have real here, and we have imaginary there. We get this straight from here. And what we can deduce from this is two equations which we can further simplify to use for the other trigonometry functions. And what we have here, I'll show that to you guys. Using these, we have, there's a different color here. It's red. And we'll say it's e to the I theta for any angle you want in radians. Of course, we're using radians here. Cosine, you can also work in degrees if you want, but here on plus I sine theta. That's our first relationship, and using the same rotation trick, we can also deduce from that is e to the negative I theta is equal to cosine theta minus I sine theta. So using these both equations, you can add and subtract them and get more relationships and get your tangent function, cotangent, secant, and the cosecant functions. And you can make relationships between that, and it's all fundamentally, and it connects with our understanding of the current mathematics. But this is the end of this video for Euler's identity. And Euler's identity, as I said before, is an achievement of everything that we put together in mathematics. And to end it off, I'll just rewrite Euler's identity once again, if you guys haven't caught it. E to the ix on I pi plus 1 is equal to 0. And that is one of the biggest accomplishments in mathematics. And that really stands true today. For almost every mathematician, they know and they live by this, because it has 5 identities straight in it: e, I, pi, 1, and 0, the additive and multiplicative identities. But that is the end of this video. If you want more proofs or help in math, tell me down below in the comments. Leave a like if you enjoyed. Share this video with your friends. And as always, nitty gritty out.